Now that we have our heads screwed on straight about all these different types of risk and loss, let's talk about how these are used in different situations from the Bayesian perspective and the frequentist perspective to actually choose a decision procedure, F, or delta. So for the Bayesian, living in Bayes' world, you say, your perspective is, let's assume pi. We'll assume some prior distribution on theta. Remember, pi was our prior distribution on theta. Theta was a parameter for our data, the distribution of our data. So the Bayesian says the solution is to assume a prior pi. And then you're left with two cases. Case 1. The first case is you know D. You know the data. You get to observe it, and then you have to choose your decision procedure, and so you should choose F of D. You only have to choose it at the value D to minimize the Bayesian expected loss at that value using your prior, and that so you're minimizing this over this quantity, over the sort of action that you're going to take. And that's this perspective. We know D. This is the perspective for using the, maybe I should have put this up here. We know D applies to the Bayesian expected loss because this is the situation where we know the data and we have assumed a prior. So all we have to do, it's very straightforward. The only thing we have to do is minimize our expected loss. And so to the Bayesian, that's a very natural thing. Case 2, this is sometimes called conditional Bayes. Case 2, if we don't know D, we don't know D ahead of time, and we still have to choose some decision procedure. So in that case, you choose F, the whole function, to minimize the Bayes risk, lowercase r, of pi and F. And this is so in both cases here, so these are well-defined problems. We started out with just this loss function, and minimizing that was not a well-defined problem, but now we have reduced it to well-defined problems in each of these cases. We can do this minimization, at least in principle. It may be difficult, but at least in principle we have now a well-defined problem. And this makes sense. If we don't know D, we would use the Bayes risk because we would want to average over D and minimize our expected loss under those averages, averaging over D and pi. Okay, now let's think about the frequentist perspective. The frequentist says, okay, if I don't want to assume a prior pi, I don't want to put any distribution on theta. Maybe there's no reasonable prior that I could choose that wouldn't influence the outcome in some way, and that can happen. And so a frequentist says somehow I've got to work with this quantity here, this frequentist risk, and somehow I need to turn this into a well-defined problem. It's not well-defined because F is a function here, and there's not a total order. You can't just say one function is always, for any two functions, you can't get this to always be better for one or the other. So we'll see that in a little bit more detail when we talk about admissibility. But to turn this into a well-defined problem, you need to introduce, so the solution which has classically been used is to introduce a further principle to guide your choice, to make this a well-defined problem. And some of the principles which have been used is unbiasedness would be one principle that you can use. And this is perfectly fine. I mean, we started out with just the principle of trying to minimize expected loss, and now we're just introducing another principle. What am I doing here? Admissibility. We'll talk about what admissibility is in a second. We saw unbiasedness before. We'll talk about admissibility a little more later. Well, admissibility is one way to at least reject certain F's, certain decision procedures. Minimax, minimizing the maximum possible risk, is another possibility. And another commonly used principle is trying to find a procedure which has certain invariance properties. And there's a whole world. I mean, I'm not going to go into detail on minimax and invariance, and even on biasedness. There's a whole world of research here, and there are probably other principles that I haven't listed here as well. But the main thing is I wanted to give you a sense of, or at least point you in the right direction for if you're interested in pursuing this path, how these sort of fit into the big picture. So all of this was how to choose your decision procedure F under each of these perspectives, Bayesian and frequentist. And so I sort of brushed through it quickly, but let me just make it very clear why minimizing this is not a well-defined problem. The reason is because for any given F, this is a function of theta, right? You know, theta could take any range of, let's maybe just notionally, we could draw theta as if it took values on the line. This is just sort of notionally. Theta is taking values in some abstract set, capital theta, but just notionally, if you could visualize this, and in some cases it does take values down the line, for any given choice F, you get some risk function. So this would be like for F1, say, let's call it R of theta, function of theta for F1, and for another risk function, you might have something like this. Let's call that R of theta and F2. So as theta varies over all its possible values, the problem is that there are some places where this, F1 gives you a lower risk. So for some thetas, F1 is better and F2 is worse. But for other thetas, F2 is better and F1 is worse. Or, yeah, right. Wait, is that? Yeah, over here, F2 is better and F1 is worse. So it's not a well-defined thing to say choose the best F. You have to say what you mean by choose the best F when you're working when you're only working with the frequentist risk. And so soon we're gonna talk about admissibility, which would be, you might say, well, what if this one were always lower than this one? What if we had another one? Say we had another one like this that was always better. It was always had a lower risk. Let's call this one R of theta F3. If F3 always had a lower risk than F1, then you would say, well, it would be silly to use F1. Why would you ever do that? You could always use F3 and have a lower risk for every possible value of the parameter. Remember, we don't know the parameter. Theta is unknown to us. And so, since it's unknown, we could choose this, and even still, we would be guaranteed to always do better than F1. And this is called inadmissibility. When this happens, F1 is called inadmissible. So we'll look at that in more detail. I'm sort of getting ahead of myself, but I just wanted it to be perfectly clear why it's not a well-defined problem to choose F using only the risk. Okay, see you soon.